Hello, in this video we will prove the equivalence of a PDA's acceptance by empty stack in final state. That is, in the previous videos we have seen that a PDA can accept a string by empty stack and also by final state. So in this video we will prove that both the acceptance are same. That means if M1 is a PDA which accepts strings by final state, and if M2 is actually a PDA which accepts strings by empty stack, what we need to prove that any language that is accepted by M1 can be accepted by M2 also. That is, languages accepted by M1 can be accepted by M2 also, wherein M1 accept by final state and M2 accept by empty stack. So that is the proof that we are trying to do here. So yeah, we will see. So M1 is accepting by final state. So let the tuple of M1 be Q sigma delta 1 Q0 Z0 and yeah, the set of accepting states. So yeah, tau also, because it's a PDA, so tau also. So tau Q sigma delta Q0 Z0, the set of accepting state A, and tau, the stack alphabet. Now the tuple for M2, we are defining it slightly differently so that we can prove the equivalence. So along with Q, we are adding two more states. One is the start state. One, we are designing a new start state. I will tell you why. We are having a new start state named Q0 dash, and we are having an erasing state because this is accepting strings by erasing the stack completely, right? So we will be having an erasing state. So we are adding these two states extra. So Q is slightly different. Now sigma is same, the input alphabet is same. Delta 1 and delta 2, here the transition function is slightly different. Now the initial state is not Q0 but it is Q0 dash. Now the start symbol is not Z0. We are having a new start symbol X0. I will tell you why. And the set of accepting state is empty here. And see, let me write tau in between so that this representation will be a bit easy for you to understand. Now tau, this stack alphabet. So here it is tau, this tau union the X0 that we have currently added. So that is tau, and the final state, here we don't have any final state, so that is null. So because we are accepting by empty stack, not by final state, so we don't have any final states here. So these are the two tuples. So this is the tuple for M1 and this is the tuple for M2. See, in part 1 what we are trying to do is we are trying to prove that if M1 accepts a string, M2 will also accept it. And in the part 2 we will do the reverse. That is, if M2 accepts a string, M1 will also accept it. So we are doing the proof in two different parts. So this is part 1. That is, if M1 accepts a string, M2 will also accept it. So these are the tuple for M1 and this is the tuple for M2. I repeat, we are adding two extra states. One is we are adding a new start state and we are adding a new erasing state, so that when M1 reaches the final state, M2 will go to this erasing state and will empty the stack, so that when it accepts by final state, this can accept by empty stack. Now we are adding a new start symbol X0. I'll give you the reason for that when we do this. Okay. So that is the only difference, and again it has some accepting states. It is having no accepting state because we are accepting strings by empty stack. So there is no point in maintaining accepting states. Okay. So we will see what happens and how it is done. Before that, we will see the transition functions, rules for transition function delta 2. Delta 1 is the normal transitions functions that we see in any PDA. But in delta 2, for this PDA, we are having some additional transition rules. First transition rule is when you are at the start state Q0 dash, without consulting any character in the input, that is without consulting any input at all, if the start state is here the start symbol is X0, right? So when the start topper stack is x0, the topper stack will be x0. What we can do is we will move to the state q0 and the new we will push z0 over the topper stack. So this is how we reach this configuration. See, for PDA M1 initially, then initial state will be Q0 and stack top will be Z0. We are achieving that through one transition in case of M2. That is, our initial state will be Q0 dash, and without consulting any input symbol, our initial stack symbol will be x0. We will be pushing z0 over x0. See, we will show that is initially m1 is this. So initially m1 will contain the state, m1 will be in state q0 and z0 will be on top of m1. Okay, so this is the configuration for m1. So in m2, what we are doing is our initial state is q0 dash and our initial symbol in the stack is x0. And what happens is after one transition with when we see nothing of the input, that is by taking epsilon as the current character, what we do is we will do a state change. That is, we will go to q0, this particular state. x0 was the initial symbol. Now we are pushing z0 on top of x0. Now we have reached this particular configuration. The state is q0, the top of stack is z0. Okay. So we achieve this particular configuration of M1 using this. Now once we do that, all the transitions of M2 on any input character, when whatever is on the topper stack will be similar to that of delta 1, that is M1, that is Q, A, Z. I will explain. That is, once this step is done, anything that is done by delta 1 will be copied by delta 2. That is, anything that is done by M1 will be copied by M2. For example, if M1 is pushing an A and moving to state Q1, if that is what M1 does, M2 will also copy that. So what it does is it will also go to state Q1 and push A onto the stack. Now if what M1 does next is I'll write this state numbers below. Q0 dash Q0 Q1. Yeah. Now what if M1 pop this A off of the stack and go to a final state QF, what it does is it will also pop this A off of the stack and will go to the same state. We don't have any final state indication for that. That's it. Okay. So we will go to the same state. So that is what happens. That is, M2 will be copying everything M1 does. That is, M2 will be simulating M1 after this first extra step. Okay. Now what happens is, if M1 reaches a final state, that is, if M1 reaches final state, then M2 will go to QE, state QE. That is, if M1 is reaching the final state, M2 will go to the state QE, the erasing state, which is a final state. M2 will go to Q2. Not Q2, M2 will go to QE, the erasing state. That is, if M1 reaches a final state, M2 will go to QE, the erasing state. That is, if delta 2, that is when the transition is defined like this, Q epsilon. Input will be empty when we reach the final state Q, right? And whatever be the stack symbol, what happens is, whatever is the content of stack, what happens is, we will go to the state QE and we will keep on deleting or popping the symbols off of the stack. That is, this means that our Q element of the set of accepting state, that is when M1 is reaching the state Q, which is the accepting state for M1, but it is not accepting for state for S, it is a simple state for S. it's an accepting state for M1. So when we reach the M1 reaches a final state, when input is completely consumed and whatever is on the top of stack, what happens is this M2 will go to the arising state QE and will keep on popping the symbols off of the stack. Now when it is in QE and the input is empty, what happens is whatever is present in the stack, it will remain in QE and will keep on popping. That is, as long as it has some stack contents in it, it will keep on remaining in the state QE and will keep on popping the stack contents, so that stack will be finally empty. So these are the 4 steps that M2 do. M2 do. So M2 does. So what happens is M2 here is Z0 X0. Now M1 has reached the final state. So what happens is M2 will reach the M2 will go to the arising state QE and will remove Z0 first. So it will have X0. Now also it will be remaining in QE and will remain and delete this X0 also. Okay, so at the end the stack will be empty. So now I will tell you why we have put this X0 as the additional character in the stack. That is, if at all QF is deleting all the characters. For example, if QF is removing this, if M1 is removing this bottom marker symbol also, it can do that. It does it. It's completely up to M1 whether it wants to delete this bottom marker symbol also. If it is deleting bottom marker symbol also, if we haven't inserted this X0, by the time it reaches QF, this stack will be empty. So there won't be any meaning for the state QE. That is why we have inserted Z0, X0 and additional symbol to M2 to make sure that it will have something to delete at the state QE when M1 reaches the final state, so that M2 will always have something to delete and there is a significance for state QE. That is why we have inserted an extra symbol to make sure that it will have something to erase being in QE. Okay. So that's it. So these are the 4 steps. I will repeat that initially M2 is at the state Q0 dash without consulting any input symbol. When X0 is on the top of stack, it will enter the initial state of M1. That is, it will enter Q0 and it will push Z0 on top of stack. Now the configuration is almost like this. That is, the state is Q0 and top of stack is Z0. Now from there onwards, M2 is copying all the transitions of M1. Okay, now when M1 reaches final state, M2 goes to a state QE, which is the rising state. That is, when M1 is in state Q, which is a final state, set of accepting state, what happens is M2 is going to the state QE, and at QE what it does is it is keeping on repeating all the symbols in the stack. That is, it is emptying the stack. So M1 and M2 simulate the same things. For example, if we are writing the instantaneous description, initially Q0 dash is the state, we are not consulting any input symbol, X0 will be on the top of stack. In one move of M2, what happens is we will reach the state Q0 and Z0 will be pushed to, when we are applying X. Okay, when we apply X, what happens is X will be the input symbol. So when it is at Q0, it won't consult any input symbol at all. But what it does is it will push Z0 onto the top of stack. So this is what it does. Now from Z0 onwards, it will Q0 X Z0 X0. What it does is it will copy all the movements of M1 and finally it will reach the final state of M1, which is not final state for M2, and the input would have been completely consumed and the stack top will be simply Z0 X0. Now what it does is it will at state QE, what it does is when it is at QF epsilon z0, it reaches the state QE, and when the input is empty, it keeps on erasing symbols. So this is what happens, that is in from Q0 x0 in 0 or more steps. In multiple steps, what M2 does is it reaches the state QE, and input would have been completely consumed and the stack would have been empty. So this is the case of acceptance, that is when M1 reaches the final state, M2 also reaches the final state like this. Not final state, M2 empties the stack like this. So this is how we prove the part 1. So hope this is clear. Now we have to prove the part 2, that is the opposite, that is if M2 is accepting by empty stack, M1 should also be accepting the same string by final state. So we can define the tuple for M2 as Q sigma delta 1 Q0 Z0, then the stack alphabet tau and the set of accepting state is null, because for empty stack we don't have any accepting state. Now we will find the tuple for M1. So M1 can be defined as Q, but we are adding extra states here, an extra start state and a final state, because M2 does not have a final state, but we need a final state. So final state, now sigma is same, delta 1, now Q0 dash is the new start state, now Z0 not Z0, we are having x0 as the new stack bottom marker symbol. Now tau contain tau and this additional x0. Now the set of accepting state is this QF that we have included here. So this is the tuple representation for M1, and this is the tuple representation for M2. So basically here what happens is Q0 will push initially push x0 onto the stack and will start from that particular state and will go to the start state of M2, just like we have done in the previous example. Now when M2 empties its stack, M1 will go to its final state. That is how it is creating that. For example, if this is M2, in the first case the initial symbol is Z0 on top of stack and the state is Q0. Now it is pushing A onto the stack and moving to another state Q1. It will be like this. Now it is if it is popping this A off of the stack and moving to Q2, it will be like this. Now to reach the final state or to accepting state, it will pop this Z0 off of the stack. So what M1 can do here is M1 can start from Q0 dash the extra state with X0 as the first symbol. Now it can go to Q0 by pushing Z0 over X0. Now what happens is, if it is from this step onwards, M1 can copy everything that M2 does. So X0 is Z0 and it can simulate M1, M2. So A is pushed onto the stack and state is Q1. Now it can pop this A off of the stack and it can be like this. Now when Z0 is on top of stack, it can go to the accepting state. Okay, because when Z0 is here, this is popping the Z0 also. So that means this particular thing is popping this Z0 also, because it is accepting by empty stack. In that case, we will have something in the stack. X0 will be still there in the stack and we can go to the accepting state QF when X0 is found. That is why we are inserting X0 in the beginning, because we can identify that when we have X0, the additional symbol which M2 does not have, when we have X0 at the bottom of the stack, we can reach the final state QF. That is why we are pushing X0 onto the stack. Otherwise, we will not identify. We will find it difficult to identify the point at which you can go to the final state. So since we are adding an additional X0, when X0 is found at the top of stack, we can move to the final state. That is why we are doing this. So it is almost like that of the previous part. The only thing is that M2 is accepting here and we are simulating M1 so that it will behave just like M2. Okay. So the transition functions for delta 1, that is this here, this can be defined as delta 1 of q0 dash comma without consulting any input at all. If x0 is on top of stack, it can go to q0 with z0 inserted onto the stack. So this is the first thing that we did here. Okay, now the second thing that we can do is, from there onwards we can simulate all the transitions done by, that is, we can simply copy everything done by M2. That is, for any state Q and any character A and any stack content Z, we can simply copy the transitions done by M2, so that we can get the similar behavior here also. Okay. Delta 1 reaches a state, some state Q with input epsilon, with input empty, any state Q, and when the input has been completely consumed, and when it see x0 on top of stack, it can go to the final state with the x0 popped off, or it can retain x0 as it is, or it can pop the x0 if it wants, or it can retain it as it is. Anyway, when it sees x0 on the top of stack, when the input has been completely consumed, it can go to the final state. So this is how we can simulate the behavior of M1, behavior of M2. So everything M2 dash is copied by M1 from in the middle portion. That is, for the first step, we are putting an additional x0, so that when we see x0 on top of stack, we can go to the final state. All the steps in between are completely copied from that of M2. So we can ensure that whenever M2 empties the stack, M1 has x0 on top of it and go to the final state by seeing that x0. So and by part 2, we proved that whenever M2 accepts a string, M1 can also be made to accept that string. By part 1 and part 2 taking combined, whenever M1 accepts something, M2 can also be made to accept it. Whenever M2 accepts something, M1 can also be made to accept it. That is, M1 and M2 are equal. That is, a PDA can accept the same string by empty stack or final state, or empty stack acceptance and final state acceptance of equal computational capabilities. So hope this is clear. Thank you.